Namaste dear learners. We now know that a current carrying wire produces magnetic field. But when a current carrying wire is placed in an external magnetic field, it experiences a force. This phenomena can be used to understand the working of the electric motor. In this session, we will try to understand the working of a generator which is based on the phenomena of electromagnetic induction. Now let us imagine a situation in which a conductor is moving inside a magnetic field, or a magnetic field is changing around a fixed conductor. What will happen? You will be surprised to know that a current is generated. This was first studied by the English physicist Michael Faraday. In 1831, Faraday made an important breakthrough by discovering how a moving magnet can be used to generate electric currents. Remember, a galvanometer is an instrument that can detect the presence of a current in the circuit. The pointer remains at 0, that is the center of the scale for zero current flowing through it. We'll perform a small activity. I have taken a coil of wire which is having a large number of turns. I have connected the ends of the coil using these crocodile clips to a galvanometer. I am going to take a strong bar magnet. The white dot represents the North Pole, and I am going to move this magnet to and fro towards one end of the coil. Let us see what happens. You will observe a momentary deflection in the needle of the galvanometer on both sides of the zero. This indicates the presence of current in the coil AB. The deflection becomes 0 the moment the motion of the magnet stops. It is thus clear from this activity that motion of a magnet with respect to a coil produces an induced potential difference, which sets up an induced electric current in the circuit. Now, if we take two different coils of copper wire having large number of turns, maybe 50 and 100 turns respectively, connect the coil 1 having large number of turns in series with a battery and a plug and a key. Connect the other coil, coil 2, with a galvanometer as you can see on your screen. Plug in the key. Observe the galvanometer. We will observe that the needle of the galvanometer instantly jumps to one side and just as quickly returns to 0, indicating a momentary current in coil 2. Disconnect coil 1 from the battery. You will observe that the needle momentarily moves but to the opposite side. It means that now the current flows in the opposite direction in coil 2. Coil 1 is called the primary coil and coil 2 is called the secondary coil. As the current in the first coil changes, the magnetic field associated with it also changes. Thus, the magnetic field lines around the secondary coil also change. Hence, the change in magnetic field lines associated with the secondary coil is the cause of induced electric current in it. This process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. In practice, we can induce current in a coil either by moving a magnet in the magnetic field or by changing the magnetic field around it. Well, it is convenient in most situations to move the coil in a magnetic field. The induced current is found to be the highest when the direction of motion of the coil is at right angles to the magnetic field. Time for another rule, Fleming's right-hand rule, which states stretch the thumb, forefinger and the center finger of your right hand such that they are perpendicular to each other. If the forefinger gives the direction of magnetic field and thumb shows the direction of motion of conductor, then the center finger will show the direction of induced current. This is a simple rule and this is known as Fleming's right hand rule. In an electric generator, mechanical energy is used to rotate a conductor in a magnetic field, and what is generated? Electricity. An electric generator consists of a rectangular coil ABCD placed between two poles of a permanent magnet. The two ends of this coil are connected to two rings R1 and R2. The two conducting stationary brushes B1 and B2 are kept pressed separately on rings R1 and R2 respectively. The axle may be mechanically rotated from the outside to rotate the coil inside the magnetic field. Now the outer ends of the two brushes are connected to the galvanometer, which is going to show us the presence of current in the circuit. Let us suppose that the arm AB moves up and arm CD moves down in the magnetic field produced by the permanent magnet. Let us say that the coil ABCD is rotated clockwise in this arrangement. By applying Fleming's right hand rule, the induced currents are set up in these arms along the direction AB and CD. Thus, the induced current flows in the direction A, B, C, D. This means that the current in the external circuit is from B2 to B1. After half rotation, CD starts moving up and AB moving down. As a result, the direction of induced currents in both the arms change, giving rise to the net induced current in the direction DCBA. The current in the external circuit now flows from B1 to B2. Thus, after every half rotation, the polarity of the current in the respective arms change. Such a current which changes its direction after equal intervals of time is called alternating current or AC, and the device is called an AC generator. To get a direct current DC, which does not change its direction with time, a split ring commutator must be used. Thus, a unidirectional current is produced, and the generator which produces the unidirectional current is called the DC generator. The difference between direct and alternating currents is that the direct current always flows in one direction, whereas the alternating currents reverses its direction periodically. An important advantage of AC over DC is that electric power can be transmitted over long distances without much loss of energy. Children in our homes, we receive the supply of electric power through the main supply, which is generally called mains, through overhead electric poles. One of the wires in the supply, usually with a red insulation cover, is called live wire. That is the positive. Another wire with black insulation is called the neutral wire or the negative. In our country, the potential difference between both the live and the neutral wire is about 220 volts. Often two separate circuits are used in our houses. One with 15 ampere current rating for appliances with higher power ratings such as geysers, air coolers, etc. And the other circuit is 5 ampere current rating for appliances like fans, bulbs, etc. The earth wire, which has an insulation of green color, is actually connected to a metallic plate which is buried deep inside the earth near the house. Let us observe a regular plug that you must have seen in your households. It's a 3-pin plug. This is connected to the earth wire. One of it is marked as live, which means the red wire, and one of it is marked as N, which means the neutral wire. And now let us see that inside this huge big plastic wire, inside this huge wire actually there are these three wires which I just talked about. The black wire, which is the neutral wire, the red wire, which is the live wire, and this green wire is the earth wire. The earth wire, which has an insulation of green color, is actually connected to a metallic plate which is buried deep inside the earth near the house. This is used as a safety measure, especially in those appliances that have a metallic body. For example, electric press, toaster, table fan, refrigerator. The metallic body is connected to the earth wire, which actually provides a low resistance conducting path for the current. Thus, it ensures that any leakage of current to the metallic body of the appliance keeps its potential to that of earth, and the user may not get a severe electric shock. In every circuit, there is something called an electric fuse. Now, a fuse in a circuit prevents damage to the appliances and the circuit due to overloading. Now, you must be wondering, what is overloading? Overloading can occur when the live wire and the neutral wire come into direct contact. This occurs when the insulation of the wire gets damaged, as I just showed you a minute back. In such a situation, the current in the circuit abruptly increases, and this is called short circuiting. The joule heating that takes place in the fuse melts it to break the electric circuit. Overloading can also occur due to an accidental hike in the supply voltage. Sometimes overloading is caused by connecting too many appliances to a single socket. Now, can you think, why should we not touch electrical appliances with wet hands? Can you imagine a household circuit without a safety fuse? Why do electricians wear rubber sandals and rubber gloves while doing any sort of electrical work? In case of electrical fire, is it advisable to use water for extinguishing fire? I don't think so. Can you reason it out? That's all for this session. Till next time, be safe, stay healthy, and keep practicing. Namaste.